All right, so let's see how you did. Example 7b, very similar to the warm-up. The numerator, are we going to do anything with it? No. Okay. The numerator is really only of interest to us if it has an even root in it. Or remember, a fractional exponent with a denominator that's even, like 1/2, 1/4, 1/6. So the denominator is where everything's happening, right? We have a variable and we have a square root. So again, if we get in the habit of labeling, here's the radicand. X plus 5 is greater than or equal to 0. X is greater than or equal to -5. That was a pretty easy one to solve, but I'll still check, right? Something bigger than -5, like 0. If I plug a 0 in right here, I get 0 plus 5 is positive. Who cares? It works. Good. All right, and now the denominator, we take the entire denominator. And again, notice we have a little helper down there outside the radical. It's -2. We say it's not equal to 0. We isolate the radical first before we square both sides. And now when you square both sides, you get 4. And right there, even though I didn't show that I squared both sides, in my head, I know that's what I did. So it triggers these asterisks, which are going to remind me to test for extraneous solutions, right? So now if you solve, you get x cannot equal -1. Now, -1 is greater than -5. If -1 had not been greater than -5, you wouldn't even really need to test it out to see if it's extraneous because it's already excluded. But it is bigger than -5, so we need to check it out. So when we do that, we plug it back in up here. We're claiming that -1 causes a 0. Okay? Let's see if it does. -1 plus 5 is +4. The square root of 4 is 2. 2 minus 2 is 0. Yeah. So it does cause a 0. Now, notice that this radical is already here. Some people want to do plus or minus. Because the radical is already there and there's an indicated plus sign out front, you only take the indicated root. It's only plus or minus when you take the square root of both sides. All right, so -1 is not extraneous. It actually causes a 0. So we'll write our domain D sub Q or DQ, right? Hunger Buster, Blizzard, Dude Sandwich. Oh, goodness. Lunch can't get here fast enough. X is greater than or equal to -5, comma. X cannot equal -1. And, of course, if you're the interval type, you could say it is beefy bracket -5, comma, -1, parenthesis, union parenthesis, -1 to infinity. All right, so if you notice the difference between the A where it was extraneous and B where it's not, notice in the denominator on A it's +1. So you're taking the positive square root, adding a number to it, and checking to see if it's 0. That's probably not going to happen. But on Q, on part B, it's -2. So that's the difference. Because it's -2, you're going to be making it smaller, a positive number, which could potentially make it 0. All right, so you can kind of pick up on that nuance before you even start and maybe anticipate if it's going to be extraneous or not. But in general, if you just check at the end, you'll be in good shape. All right? What's that? Yeah, it's not extraneous, so I included it. Right? It does cause a 0. That's what we're checking for. Extraneous means it doesn't cause a 0. Like this one, when I plugged in a 3, it wasn't causing a 0, and so I don't need to exclude it. In this case, -1 did cause a 0. It was not extraneous, and therefore I do need to exclude it. I know it's a lot to keep track of, right? We're trying to find the values that cause a 0 in the denominator. Just keep that in mind. All right, how about this guy? It says to verify on your calculator. We'll see if we have time for that. Do we have a denominator here? Or any negative exponents? No. But we do have a square root. So let's go ahead and do the radicand, and it's x squared minus 4, and we say it's greater than or equal to 0. Okay? Take 1 minute on your own and solve that inequality. You're on a deserted island. No one's telling you how to do this, but getting off the island depends upon you being able to solve this inequality. Pressure's on. There's a lot at stake. Maybe you like the island. Maybe you want to stay there. If you get it right, you have the choice of leaving. Let's say that. As I suspected. What's that? You're going to stay on the island? There you go. I see a lot of people doing as I suspected they would do. Is anybody? You're. That's better. Kinda, yeah. You're on a good, you're a decent start. I would kind of go from left to right. Yeah, smallest to greatest. It needs to be positive, right? It needs to be positive. So what you need to do is actually, if you're doing it this way, you need to check the values in between those two. Where is it positive? Where is it negative? Oh, there! That's a great start. Yes, now keep going. Yours method will work as analytic. Your method is the way that I taught you all the other day. Correct. It comes down to figuring out what that number is and that number, because that's the divider between positive and negative. See? You got the graph. Yes, yes. So you need to figure out what the X-intercepts are, because those are the gatekeepers between positive and negative. Good. What type of inequality do we have? Is it linear? No. We can solve linear inequalities algebraically, but there's that caveat. We have to remember, it doesn't always work. I have to multiply or divide by negative when I flip the sign, or the other way around. I have to flip the sign when I multiply or divide by negative. Can we solve quadratic inequalities algebraically? No, I told you in class we can't. You either have to test intervals analytically, or the way I want y'all to do it, we solve it graphically, right? So let's do that. Graphically, this is reviewing parent functions. Your parent function for that is the x squared. So let's draw x squared. I'll draw it first, and with notability I can do this. And then, of course, the minus 4 does what to that graph? Moves it down 4, because it's outside the squared. It's affecting the y values. So 1, 2, 3, 4. Boom, there it is. Right there. There's negative 4. Okay, now look. If you have your graph, those y values, you can clearly see where they're positive and negative, right? These y values are positive above the x-axis and negative below the x-axis. The inequality says for what values of x is it greater than or equal to? Is greater than above or below the x-axis? Above, right? Greater than, bless you, means positive. So here in these highlighted regions are where the graph is positive. It's always going to come down to the x-intercepts of the graph. Are my positive y values between the x-intercepts that I've marked in red, or outside the x-intercepts? Outside of it, right? So on the number line, I would shade to the left, because everywhere to the left of that, my graph is above, and everywhere to the right, it's above. So how do we find those x-intercepts? I need to know what those numbers are. Well, for a problem like this, you could probably just look at it and figure it out. But if you're not sure, go off to the side and set it equal to 0, not greater than 0. Set it equal to 0, and then solve, right? This is how we find x-intercepts. So some of y'all factored that, x minus 2, x plus 2. We keep it equal to 0, and you get your x-intercepts to be plus or minus 2. So if you could just figure out what they are by looking at it, that's great. So we're going to solve these graphically. If it's a parabola, it's either going to open up or down, depending on the leading coefficient. And all you have to do to find the x-intercepts is set it equal to 0. Your final answer, then, is always going to be one of two things. It's either going to be outside the x-intercepts, like this case, or if the parabola had opened downward, it would be everything between the x-intercepts. And so our final answer, then, is going to be the following. It's going to be the domain of P is going to be the set of all x such that x is less than or equal to negative 2, or x is greater than or equal to positive 2. This is what we call the disjoint interval. Disjoint means there's no overlapping. It's one or the other. It's either to the left of negative 2 or to the right of positive 2. And because it's one or the other, we always write it as two separate inequalities, one or the other, okay? If you were doing interval notation, it would be negative infinity to negative 2. Would I put a bracket or a parenthesis around negative 2? A bracket, because I could say it's greater than or equal to. So at negative 2, it's equal to. So I would put a bracket. And then union bracket, I would pick up at 2 and go to infinity. So that's how you would do that one. All right, so heads up here, you would not do it like this. You would not say 2 is less than or equal to x is less than or equal to -2. So notice if you write it like this, the alligators are eating the correct thing, right? It's the alligator's eating the -2 and the alligator's eating the x. But this is bad math, okay, because it's not written from least to greatest. We call that the compound inequality up above. So we have to reserve that for the and case. If it were between these two, it would be the compound inequality. But if it's the disjoint interval where there's no overlapping, you write it as two disjoint inequalities, one of them or the other one, okay? All right, there you go. How are we going to solve quadratic inequalities? Graphically, okay? So with that in mind, D is now yours. It is good, or M for short, okay? Find the domain of good of X. Think you could explain these next period? Yeah? Okay, all right. Use the previous one as your template if you get stuck. I see a lot of good-looking parabolas. They're frowning. That's not so good. But I know they're just being sarcastic when they're frowning in here. They're really smiling on the inside. Good. Downward opening parabolas. Your parabola, look at the coefficient of x squared. It's what type of number? Yeah, this is 4 minus x squared or negative x squared plus 4. So what would the negative in front of the x squared do to the graph? Remember, negative parabolas open downward. Positive x squareds open upward. Negative x squareds open downwards. So it's going to actually flip and open downward, and then the plus 4 moves it up 4. Yeah, so it opens downward. Yeah.
Okay, I just caught on that.
Okay.
What I was going to say, I forgot, like, what all of them meant. Are we allowed to say that? Like, just like that?
Mm-hmm. I want you to show the inequality first. So 4 minus x squared is greater than or equal to 0.
Okay.
Okay. Then you're going to have to find the x-intercepts. So you can either see what you did here, which is okay. You can either factor it with the inequality in place, or you can set it equal to 0 and find the x-intercepts however you want. Okay. But once you have the graph and you know what those two x values are, it's either going to be between the x-intercepts or outside of them.
So how do you know if it's disjointed or if it's just in the middle?
If it's in the middle, like in this case, which one do we want? We want it to be greater than or equal to 0. So greater than or equal to 0 is going to be above or below the x-axis. Above, right? So in this case, it's this interval here. So this is the connected interval. It's between the two.
Oh, okay.
Okay? You know if it's going to be above or below by looking at your inequality. If you're finding domains, the plus 4, that's a plus 4 in front, right? It moves it up 4. For domains, because you always want it to be greater than or equal to 0, you want to know where is that graph on or above the x-axis. On or above the x-axis. So again, for parabolas, it's either going to come down to, is it between your two x-intercepts, which would be the connected compound interval, or is it outside the x-intercepts, which would be your disjoint, two separate inequality intervals? All right, let's do it together then. Some of y'all are done. The 4 outside the radical and the minus 4 outside the radical, not a real concern. There's no denominator, but there is the square root. So here's again what I expect to see. 4 minus x squared is greater than or equal to 0. Now from there, if you want to sketch the graph, That's fine. It's a quadratic inequality. So I'll go ahead and do that kind of off to the side down here. If you want to help yourself, rewrite it. Instead of 4 minus x squared, write it as negative x squared plus 4. That's kind of the standard form that y'all had in Algebra 2. So the parent function is the parabola. The negative in front is going to reflect it across the x-axis, which means it opens downward, and then the plus 4 moves it up here to 4. So there's the vertex, and then it opens downward, and then symmetrically downward. Okay? Now, if you look at your inequality, it says I want to know where that graph is greater than or equal to 0. So a lot of y'all identified it correctly. It's going to be at this point, and then everywhere between them. So on the number line, I would shade like this. This is your connected case, not the disjoint case. So I need to find those x-intercepts, right? Now, in the previous problem, what I did is I actually went off to the side, and I set that equal to 0 to solve it. But if you would like, you could factor it right here. That's 2 minus x, 2 plus x. And you could say that that's still greater than or equal to 0 because the line above is equal to the line below. And now you could just look at your factors and probably discern what the x-intercepts are, right? What value of x when you plug it into the first one gives you 0? 2, so that's this one. What value of x when you plug it into the second factor gives you 0? Negative 2, okay? Now I'm going to come back to that line here in just a second. So now that you have your x-intercepts and you know that you want it between the two, now you'll say the domain of M is going to be the set of all x such that. So here's a cool way to think about it. If it's a connected interval, we're looking for these values of x, right? I'll just label that x. Where I shaded is x. Notice that x physically falls between the two numbers negative 2 and 2. So that's all you have to do in your inequality. Watch this. Negative 2, x, and 2. See how it falls in between there? Just like up here. And these are going to be less than or equal to's on both of them. That's your AND case. This is your AND case, which is your also connected case. It's not the OR case. It is possible to be both bigger than negative 2 and less than positive 2 at the same time. All right, so anytime you're shading two lines and they're touching, they're connected, it's the AND case. If you're sketching away from each other and there's no overlapping, that's two separate inequalities, they're disjoint. Okay, so the real way to read this is not necessarily from left to right. You read these compound inequalities kind of from the middle out. So you would say x is greater than or equal to negative 2, and x is less than or equal to positive 2. Now, if you're not sure if that's the right interval, pick a number between negative 2 and 2, like 0. I'm saying 0 should work. If I plug in a 0 up here for x, I get 4 minus 0 squared. That's 4. The square root of 4 works, okay? And if you want to then pick a number outside of negative 2 and 2, like 3, 3 should not work. 3 squared is 9. 4 minus 9 is negative. Got it, right? Now, let me show you the common mistake that students make. Okay, this is a mistake alert. Mistake alert. They factor it like that with the inequality, and then, like it were an equation, they would say then 2 minus x is greater than or equal to 0, or 2 plus x is greater than or equal to 0. This would be an algebraic approach. That gives you then that negative x is greater than or equal to negative 2, which means x is less than or equal to 2, or x is greater than or equal to negative 2. Is that right? Is that actually what we want? It is, right? This actually worked. It's giving you the same intervals. Do you think it's always going to work? No. Let me prove that point. Let's come back over here. If I would have done it over here, I would have had x minus 2, x plus 2, greater than or equal to 0. If I then said both of those, x minus 2 is greater than or equal to 0, or x plus 2 is greater than or equal to 0, I get x is greater than or equal to 2, or x is greater than or equal to negative 2. Wow. Well, if you look at the number line, how that would work, here's negative 2. We would shade it solid, and we would sketch to the right. Here's positive 2. We would put a dot and sketch to the right. And so if you know from number line graphs, you would only take the overlapping region that satisfied both, you would get an answer here of x just greater than or equal to 2, which we know wasn't the answer. Notice our answer was also everything smaller than negative 2, which we don't pick up from the inequalities, right? So you cannot solve quadratic inequalities algebraically. This line is okay. If it's completely factored and it's still greater than or equal to 0, that's okay. Where it breaks down is when you set both of them then greater than or equal to 0. That works with an equation. It doesn't work with an inequality. So it didn't work here. Even though it did work here, this line would be bad. Remember we said in mathematics, it can work for every value in the whole wide world except 1. And if there's just one for which it doesn't work, we say it doesn't work in general. All right? So don't take each of your factors and just say they're greater than or equal to 0. How do we solve quadratic inequalities? Graphically. All right? Graphically. Sweet. Any questions on that? All right. Forging ahead. EST or S of t. S of t, S of t. All right? Any concern about the numerator? No. But the denominator has both a variable and a square root. So let's just do what we've been doing. The radicand is 3 minus t squared. We want that to be greater than or equal to 0. And then I'll go ahead and set up the denominator. We want the entire denominator, 3 minus 2t squared, to not equal 0. So if you want to set those things up, there's 2 checks right there, right? On a quiz or free response. We've been doing that for the last 2 days. All right, let's go ahead and solve these then. This is a what type of inequality on the left? If it's squared? Quadratic. How do we solve that, bless you? Graphically. All right, so again, all you have to do is come off to the side, quickly sketch a graph. If you want to rewrite it to help yourself, that's a negative 2t squared plus 3. The negative in front is important because that means the parabola is going to open what? Up, down, left, or right? Down. The 2 is just going to stretch it vertically. We don't have to show that necessarily. And then the plus 3, as we saw before, moves it up 3. So to sketch it, you could just come up here to 3, and then just draw a parabola opening downward. And now we want to know where is it greater than or equal to 0. So once again, greater than or equal to 0 is going to be on or above the x-axis. It's going to be the connected interval between the two. So as always, it comes down to finding the x-intercepts. Now, does 3 minus 2t squared factor nicely? No. So in this case, I'm not going to factor it and say it's greater than or equal to 0. I'm just going to come down here and set the equation 3 minus 2t squared. I'm going to set it equal to 0. Because if it's equal to 0, we can solve by our old methods. We could factor and set each equal to 0, or we can isolate the t squared, which is what I'm going to do. So I get 3 equals 2t squared if I bring that across. If I then divide by 2, I get 3 halves equals t squared. And now how do I solve for t? Square root it, but I have to remember to consider, well, not an extraneous, because I'm not squaring both sides. I'm square rooting both sides. You only have to check for extraneous when you square both sides. But we have to consider plus or minus, right? And we know that, right? We're thinking through the problem. I know there's 2 x-intercepts. And because it has y-axis symmetry, they should be symmetrical. So it's plus or minus the square root of 3 halves. Not a friendly number, but that'll work, okay? So we have 2 of them. So now that I know what these numbers are, this number here is negative square root of 3 halves on the x-axis. This one is positive square root of 3 halves. I have all the information I need now to answer the question for this piece. For what values of t is this graph on or above the t-axis? It's going to be everything between the two, right? So again, if it's the connected interval, just throw your independent variable there, and then you could say negative square root of 3 halves, less than or equal to t, less than or equal to positive square root of 3 halves. Or as an interval, you could say this, negative square root of 3 halves, comma, positive square root of 3 halves. But notice that's just the demand of the radicand. All that work was just for the radicand. We still have to consider division by 0, right? Which we've had a problem like this before. If we just square both sides now, and then isolate it, we get t squared cannot equal 3 halves. When we take the square root, we get t cannot equal plus or minus the square root of 3 halves. So when your entire denominator is just the radical, it's going to come down to you can't use those numbers. So what's the easiest way to combine the two results? If this one says it can be equal to the endpoints, and this one says it can't be the endpoints? Yeah, change the inequalities from less than or equal to just less than. That's the easiest way to get rid of those values, okay? So that's the efficient part. So we'll say then the domain of our function S is the set of all variables, what? P. If you said X, I wouldn't count off, because that's what we typically use. It's a set of all T, though, such that it's between negative square root of 3 halves less than T less than positive square root of 3 halves. Again, that's your compound inequality. We took the equal signs away because the denominator said they caused the 0. If you're doing interval notation, negative square root of 3 halves to positive square root of 3 halves. Now, you do have to be careful with interval notation because if you're not paying attention, you might mistake the interval from negative root 3 halves to positive root 3 halves as a what in this case? What else do we write like this with parentheses and a point on a graph, right? An ordered pair, but it's not. It's an interval. So that's why it's important that it follows D sub S. Now we know it's a domain, or remember you can even clarify it even more by in front putting T epsilon, which means your independent variable is in that interval, okay? All right. Questions so far? Just kind of more the same, more the same. We're kind of refining our techniques a little bit. We're making ourselves aware of certain things as we go so that we can become more efficient. Now we're going to do letter F, okay? Letter F. Doesn't that look fun? It does look fun. Yeah, it looks fun. Right, yeah. So on letter F, the function's name is U of N, right? Fun, fun, fun. All right, so we need to find the domain. Yickety yikes. Oof. What type of fraction have we there? A fraction within a fraction, which we call complex fractions, right? You can call them compound, but make sure I'm out of the room, right? Complex fractions. I think Mr. Johnson knows that time where that story I told you about snapping my radius in ulna and it's sticking out of my arm on Craig's skateboard ramp in the rain. My parents were out of town, and I held my arm together for hours and hours without pain med until they got a hold of my uncle. So that's a complex fracture. So we call them compound fracture. So we call them complex functions. Okay. Complex fraction. Sorry. My bad. I'm just reliving the nightmare. PTSD. Sorry. It says to verify your calculator. We're not going to need to. You are the calculator. What do we do first? We're finding domain. Do you see any radicals, square roots, fourth roots, or any fractional exponents? I don't either. So I think we're okay in terms of the radical. The only other thing is division by 0. Do you see any denominators? Oh, yeah. I see a lot of denominators, okay? The first denominators that I always refer to, like if we were to clean up this complex fraction, are the miniature denominators. It's kind of a cute way to say it, right? The miniature denominators. So we skipped this for this test, so this will be on the next test. We're going to come back. If you were to clean this up, you would multiply by 2n over 2n. That's the LCM of your miniature denominators. But we're not going to do that. We want to find the domain. So there's your miniature denominators. But, George, you said you saw lots. Where is there another denominator? Very good. The entire thing in red is itself a denominator, okay, of the bigger fraction, okay? So let's go ahead and work on the miniature denominators first, okay? Denominators. If you want to put mini denoms, that's kind of cute, right? Mini denoms. I got n cannot equal 0 and 2 cannot equal 0. Well, the second one's a given, right? It's a constant. 2 is never 0. So I don't need to consider that. So all I got to do is say n can't equal 0, and then I solve for n. Done. That was easy, right? Done. I solved for n. So n can't be 0, right? And you don't have to check because we didn't square anything. You plug in a 0 for n, and you're going to get a 0 in 2 different places. All right? So now let's look at the big denominator, which is n minus 1 all over n. That whole thing can't equal 0. Now, here's the first time that we've had a fraction equal to 0. In algebra, your teacher probably told you to solve this by doing what? Multiplying both sides by n. That's yucky, yucky, gross, gross. You do not want to do that. Because in an equation that you're trying to solve, if you lose variable information from the equation, you're losing potential solutions. So don't multiply both sides by n. Here's what you want to do instead, okay? Think about it this way. A fraction, like n minus 1 over n, is equal to 0 when just the numerator equals 0. Right? 0 over 5 is 0. 0 over 10 is 0. 0 over 0 is not 0. Okay? So it's going to end up giving you the same thing as if you multiplied both sides by n. But we're going to get to that by a different logic. n minus 1 over n is equal to 0 when the numerator n minus 1 is equal to 0. Okay? That's what we're doing. So we're not getting rid of the n. We just realized that it's not important for the 0. All right, so now you solve for n, you get n equals 1. Now you might want to quickly check. When n is 1, does it make the denominator of this one 0? No, it makes it 1. So essentially when you plug in a 1, you get 0 over 1. And what's 0 divided by 1? 0, right? So a fraction is equal to 0 when the numerator is equal to 0. So there is your other taboo value. So how many values are off limits? Yeah, just 1 and 0, and we've already tried them out. So to write our domain here, we'll say the domain of u, that's the passive voice, right? We should just say your domain, that's a different class, is the set of all n such that n ain't, and you could just list them, 0 and 1, 0, comma 1. There you go. Now, I haven't showed you how to clean that up yet, but maybe we'll pick up there tomorrow with the second verse to the same story. If you were to clean up this complex fraction and then find the domain, and I'll show that to you tomorrow, you're going to get a different domain. Okay? So you always need to find the domain first, and then if you wanted to simplify it, you can. You don't simplify first and then find the domain. All right, so make sure that you're practicing on the worksheet. This is the last of the domain stuff. We're going to now talk about discontinuities, and we'll finish tomorrow. So have a splendid National Peanut Day, everybody. And keep washing your hands. There's hand sanitizer over there. Try not to spread germs.